message coming from my eyes says leave it alone.
Information from net ionic and ionic equations into something we can use in solutions. So we have two solutions. One that is 25 mils and 0.100 molar NaCl. And we have another solution that is 30 mils of a mercury nitrate solution, mercury 1 nitrate solution. And that's a 0.230 molar solution. And you mix the two, and they ask us how many grams of mercury chloride will precipitate. Mercury 1 chloride. Well, we know mercury 1 chloride precipitates because we can use our solubility rules to predict that. If you take the sodium chloride plus the mercury nitrate, the mercury 2 chloride will precipitate out based upon our solubility rules. 2 sodium chlorides, 2 sodium nitrates, done. And this is a balanced chemical reaction. If we had been given grams, we'd take the grams of the sodium chloride and the grams of the mercury nitrate and then figure out the chemistry from there. And how we would do that? Well, this is a limiting reagent problem. How do we know that? They give us two quantities of material. Well, they give us the amount of sodium chloride and the amount of mercury nitrate. But it's hidden in there. They don't tell us exactly how much of each. As a general tip, one of the ways you can do this is to, given any sort of information regarding the two quantities, convert both of them into moles. So one strategy is to aim for moles of each material at the start, and then use that as your starting point for your limiting reagent calculations. So how would we do that? For the case of the sodium chloride, we know that there are 25 mils of the sodium chloride solution, and then using our molarity, because a volume and a molarity together are used to obtain moles, we can simplify 1,000 mils. A liter of sodium chloride solution contains 0.100 moles of sodium chloride. Again, this is just a restatement of the molarity statement. Moles per liter. And once we have that, we can figure out the number of moles of sodium chloride. You should be able to do the same calculation for the moles of mercury nitrate. I'll let you set that one up yourself. 2.5 times 10 to the minus third moles of sodium chloride. And then if you do the same calculation for the mercury nitrate, you find that you get 6.9 times 10 to the minus third moles of mercury nitrate. Now, once we have those quantities, we can then figure out which one's the limiting reagent using our standard methods. We know that for every 2.5 times 10 to the minus third moles of sodium chloride, we know that for every 2 moles of sodium chloride, that is equivalent to 1 mole of mercury 1 chloride that precipitates out. Now, we could continue on to the gram if we so desired, but we're fine working in moles, so this would be 1.3 times 10 to the minus third moles of mercury chloride would be produced. And you can do the same calculation for the mercury nitrate. That gives us 1 mole of mercury chloride, mercury 1 chloride, and we get out 6.9 times 10 to the negative third moles of mercury chloride. So what this shows is that we produce less mercury chloride, so that means this is our limiting reagent. We then use our limiting reagent to start the calculation. In fact, we can then take this 2.5 times 10 to the minus third moles and then figure out how many grams of mercury chloride will precipitate. And you should be able to do that calculation and obtain 0.613 grams of mercury 2 chloride. All right. I'll let you set that one up for yourself, but it should be starting with the sodium chloride. Or if you're astute, you know that you've done half the work already. All right. So these solution precipitation problems are very germane, and limiting reagent problems look no different when you have components. The best bet, again, is to try and shift things into the mole, and then using that mole-mole relationship that we've grown used to, grown to love, we can then carry on the calculation. Now, one example of calculations like this that aren't explicitly limiting reagent problems, but rely on this stoichiometry, A plus 2B going to C, there's an underlying assumption is that when the amount of A is just enough to use up all of the B, the stoichiometric amount, at that point, there's no leftover material when a reaction is stoichiometric. So we can use this fact when we do like acid and base titrations. You add acid to the base up until the point when there's base and acid are equal. The moles of base is exactly enough to cancel out the moles of base. Up until that point, there will always be an excess of one or the other. At that point, there will be an excess of neither. And when you go past it, there will be excess of, say, acid, for instance. You can use this presence of excess to tell you when the titration is done, either in terms of the excess reagent or excess after the reaction, using what we call an indicator. An indicator usually is a color-specific material that changes depending on the pH or amount of acid in solution or base in solution. And so when all of the acid is gone, the color changes, and we can use that as a measurement of the end point. Though reality, we really want is the equivalence point, the point when the moles of acid is equal to the moles of base. The moles of one reagent is exactly enough to cancel out the moles of the other. What that means is at that equivalence point, if we know how much acid was present, we then also know how much base is present. And so we can use the moles of one analyte to tell us how much is in the other one. It's a classic chemical problem, using information you can control to figure out information you can't. And that's what a titration does. In practice, titration is usually using a known volume in a burette of some sort. You usually know the volume, and you can watch that. And then once the volume changes, from that volume change, you can figure out how many milliliters were added. And from the known molarity of the material, you know the number of moles. So the volume and the molarity give you the number of moles. And once you know the number of moles of one component at the equivalence point, you then know how much of the other one is present based upon stoichiometry. Quite common. Let's try one. Titration example. All right. Many acid-base reactions, particularly those involving carbonates, can release gases. The carbonate reacts with the HCl to produce carbonic acid, which then decomposes into water and CO2, and the CO2 comes off. This is like standard baking soda and vinegar. Right? We've done it a million times. Baking soda and vinegar, it foams, and that foam is actually CO2. let's take a look at a problem. We have a sample of limestone, which is mostly calcium carbonate. Some percentage of calcium carbonate. But we don't know how much. Right? But because there's also silicates and some other materials embedded in this limestone. You can use the titration to measure how much calcium carbonate is present. If you can do this a number of different ways, you can measure the amount of CO2 that comes off, and at the point where the gas stops evolving, or more likely you use an indicator that measures excess HCl. Before you add the acid, everything in there is the carbonate, and as you add the acid is continuously consumed during the reaction until there's no extra. And at that point, until there's no extra calcium carbonate, and then all the HCl is present. So you can use a pH indicator that measures excess acid. And so, if you know at the equivalence point the number of moles of acid you used, you know how much calcium carbonate was present. So when we say percent calcium carbonate, what we're really looking at is grams of calcium carbonate compared to the grams total. Well, before we get to grams of calcium carbonate, we can get to moles of calcium carbonate. And before we get to the moles of calcium carbonate, we can figure out the moles of HCl. Lucky for us, in our problem, they give us two quantities. 760 milliliters, and 0.550 molar concentration. So they tell us that this HCl solution requires 760 milliliters, and that the molarity of that was 0.550 molar. We can then use that information for every 1,000 milliliters, that is equivalent to 0.550 moles of HCl. And then from the moles of HCl, we can figure out moles of calcium carbonate. For every 2 moles of HCl, that is equivalent to 1 mole of calcium carbonate. And then for every 1 mole of calcium carbonate, grams, 100.1 in this case, grams of calcium carbonate. So that in that sample there were 20.9 grams of calcium carbonate. Well, once we know that, we can take our actual grams of calcium carbonate and divide it by our total sample, 25 grams. Says that times 100 says that the percent of calcium carbonate in this would be 83.7%. So titration is often used to measure unknown moles of materials. A volume and a molarity together give us the number of moles. If we know the number of moles of one thing, particularly at the equivalence point, you can relate it to the moles of the other. Other cases, like this neutralization, are quite similar. So let's take a look at this problem. Standard neutralization. The neutralization of blah, 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 blah requires 25.3 milliliters of a sodium hydroxide solution that happens to be 0.133 molar sodium hydroxide. And they say that it required that much sodium hydroxide to neutralize 5 mils of an HCl solution. And we want to know what the molarity of that solution is. So even though they give us 2 quantities of this is not a limiting reagent problem. Because they didn't really give us 2 quantities. They gave us a volume. A volume without a concentration is worthless. So what kind of problem is this? And this is a what is the molarity kind of problem. So for a molarity problem like this, we're going to need to know the moles of HCl, and we're going to divide it by the volume of HCl, and that'll give us the molarity, as long as this was in liters. So even though we have this volume, which is useful, we can convert it into liters, what we really need is the moles of HCl. But the whole purpose of titrations is that at that quantity, that number of moles of HCl can be related to the volume via the balanced chemical equation. In this case, they say it's a 1-to-1 reaction. We know that 1 HCl plus NaOH goes to something and something. So, but this is a 1-to-1 reaction. We don't really care about the products, to be honest, as long as it's balanced. And they tell us it's balanced. So we know that 1 HCl gives us 1 sodium hydroxide, or requires 1 sodium hydroxide. So if we know the moles of sodium hydroxide, oh, wait a second, look at this. A volume and a molarity that we can use to figure out the number of moles. So use that volume and molarity to figure out how much sodium hydroxide is present at the equivalence point. And that means that that much sodium hydroxide, the number of moles of sodium hydroxide, is equivalent to the moles of HCl. I'll let you set that one up. Hit pause, run through the calculation, tell me how many moles of sodium hydroxide are present. Down there. Pause, 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 pause. Well, it says that if you did the calculation right, you should get 3.37 times 10 to the minus third moles of sodium hydroxide. Well, because this is a 1 reaction, we know that 1 mole of NaOH is equivalent to 1 mole of HCl. That says that in that 5 ml sample, there are 3.37 times 10 to the negative third moles of HCl. Given that, we know that 3.37 times 10 to the minus third moles of HCl for every are in 0.005 liters. This is our mole, this is our milliliter conversion over here. Convert that into liters using our standard methods. This tells us that the molarity, moles per liter of the HCl, should be 0.673 mole. Now, very typical problems. On top of that, there are redox titrations, but they are no different than acid-base titrations or precipitation-based titrations, in that they require this balanced chemical reaction, and then there's equivalence point. As long as you can measure the equivalence point, and usually in a problem that equivalence point is given to you, it says the equivalence point is, or at the equivalence point. They usually use subtle language like that. And so in those cases, it's just a balanced chemical reaction, though it may often not be 1-to-1. Particularly redox reactions, they can have really odd stoichiometries, 3 to 7, etc. There are some examples in your homework. So titrations rely on this fact that the number of moles of one thing tells you the number of moles of another when you're at a stoichiometric situation.